All right, so this has to do with pressure flow when you're looking at Moody diagrams. Realize that everything is going to be Bernoulli's equation, but when we get to open channel flow, Manning's equation and the like, the hydraulic grade line and the energy grade line will be exactly the same because there's no pressure on the surface. All right, here's what you do. First thing, you draw out the project on your sheet. On your desk, you should have a sheet of paper, a calculator, a pencil, some straight edges, and you should draw out the project at some reasonable vertical and horizontal scale. And you could also do this in your calculator quite easily, or in Excel or in AutoCAD, but you want to be able to do the kind of quick sketch pretty quick. Calculator's not bad for that if you have station and elevation information. Remember that? All right. You need to use ingrained problem-solving rules. These need to start to catch right now, if not before. In other words, use foot-pound seconds, or Newton-meter seconds, or kilogram-meter seconds, or slug-pound seconds, slug-feet seconds. You need to think about datums. You need to think about coordinate systems. You need to write down all the equations you think you might need. You need to use algebra and logic as well. You need to have a normal range of values that you expect. All those problem-solving skills that you've now used for 2.5 semesters, probably longer. You need to write out and chant Bernoulli's equation. In other words, as you write Y, you're writing the elevation head, the foot-pounds of elevation energy per pound of water. As you write P over gamma, you're rating saying the pressure head, the foot-pounds of pressure energy per pound of water. This will ingrain it in your head, and the Bernoulli's equation comes back over and over again in problem solving when you're dealing with flowing water in any form. Now look at your sketch and see if you can identify 2 separate points in the flow stream where you know something. That usually is going to be perhaps the reservoir surface and the exit of the pipe or the system. And a system could have many exits, but where you can, in essence, measure the flow. And if you know the flow and the area, you know the velocity. If you know the elevation in a reservoir, and you know the reservoir is large enough that it's not really doesn't have much velocity, then you know its elevation head, and you know the pressure head is probably equal to 0 if you're assuming that atmospheric is your datum, atmospheric pressure. If it's a free open problem, open flow problem, it's pretty easy to solve graphically if you know the velocity energy, if you know the velocity head, and you literally just draw a line between the free water surface and one velocity above the pipe center. That is your energy grade line, and then you draw the hydraulic grade line parallel to that running through the pipe center. Those are really straightforward problems, and what you see is that is the next step up from doing the calculation of the velocity of the flow being the square root of 2gh. That's assumed, that one there assumes no friction. This one here does assume that you're losing friction on a constant base, or losing energy to friction on a constant basis through the entire run of the pipe. You then realize that you're going to step down and lose a chunk of energy at any time the flow path kind of makes a weird turn, like through a fitting or in an entrance. All right, if you can't determine the flow rate, you're going to need to use something, this is very typical, you're going to need to do something called Moody's diagram, which actually is an empirical diagram gathered by figuring out how much energy is lost based on the physics of flow. You need to use, there's a calculator, there's a program in the calculator that takes advantage of the friction factor F. And the friction factor, you will see as looking at the Moody diagram, is a function of the pipe diameter, the relative roughness, the viscosity, and the velocity, which in fact you have to guess. And remember, 3 to 10 feet per second is a guess to start. It is our normal range of design flows, but very often you may be looking at flows faster or slower than that. When you look at that diagram, you have to realize that the friction factor is a function of both the relative roughness, that picks the particular curve, and the Reynolds number. So what they're describing there is a three-dimensional function where the friction factor S is a function of relative roughness and Reynolds number. The relative roughness is just essentially a ratio of the internal topography, how up and down the inside of that pipe is, and it's in the order of microns very often, depending on how rough that inside of that pipe is, that ratio to that of the diameter of the pipe. Realize there is a circular reference here, and you need to do some of these by iteration. Kind of guess and check is another way to say that. Don't forget that the Reynolds number is going to describe how turbulent the flow is, laminar or turbulent or transitional, and that in fact it is a ratio of the inertial forces and the viscous forces. It's a unitless number, and it's defined by the diameter times the velocity of flow divided by the kinematic viscosity. And you should be able to figure the units for kinematic viscosity when you know that Reynolds number is in fact unitless. And they are in the order of 1 times 10 to the minus 5th in the units that you'll need to figure. Now do the calculator punch. That will do your first iteration. You then have to take the Reynolds number that it gives you and the velocity of flow and come up with a new friction factor and go through a few times. If in fact it is a rough pipe, in other words, it has some roughness, it's not a smooth pipe, then you should be able to guess the first time on the Moody diagram what your friction factor should be. That is because the graphs flatten out at higher Reynolds numbers. If your pipe is smooth, as an HDPE or PVC pipe, you're going to need to first guess at a velocity of flow and then calculate through and definitely go through twice. What the program will give you, the calculator program will give you, is a new Reynolds number, which lets you go and re-look at the Moody diagram, which is on a semi-log basis, if you remember that from soil gradation charts. You do this 3 times, you should get to where you have a stable answer. Finally, do not forget then to graph the energy grade line and the hydraulic grade line. You will realize on that graph that the value minus the F friction factor divided by the diameter times the velocity head is the slope of the energy grade line. And so you can, the function of that looks like essentially, if you call the energy grade line Y, or your total amount of energy, it is equal to mx plus b, right? With m being that slope there, x being the distance down the pipe, and b being the starting elevation of the energy grade line, which is usually your reservoir. Realize, however, that it also steps down maybe 1 or 2 velocity heads depending, sometimes more at any given fitting, very often a little bit less than that. Very often you can ignore minor losses. That's what it is called when energy is being lost at a fitting. Once again, a program has been provided on the calculator that will do some of that graphing, and we'll go through that in class. All right, so finally, when you're looking at that graph on paper, wherever you're looking at it, you want to realize that the distance between the hydraulic grade line and the pipe is the pressure head. And that pressure head is what is going to break the pipe. The separation between the energy grade line and the hydraulic grade line, or the distance between those 2 lines, will vary depending on the velocity of flow. And if you remember what that separation is, it is a velocity head. And so as you look at different systems that have more than one pipe size, that difference between the energy grade line and the hydraulic grade line will increase or decrease depending on the velocity of the flow. Remembering that Q equals velocity times area, so if you have consistent flow and you have different areas, your velocities are going to change based on that value here. Remember, that is a ratio of areas or ratio of diameters squared, or radiuses squared. And finally, for systems that split and loop, realize that the sum of the head around one loop must be equal to 0, and the sum of the inflow and the outflow at any one point is equal to 0. Welcome to circuits. Thanks for listening.